A good day all to the second online session for EEB601 Circuit Theory. Return on to page 11. There's a circuit that I've reproduced here of the series RL circuit. But you will note the only difference is that your source voltage here is a sinusoidal waveform. It's an alternating current. Right. So to analyze this circuit, we use Kirchhoff's voltage law. So VL plus voltage drop across resistance VR is equal to the source voltage here. And knowing the fundamental equations, we can form our first order differential equation model. VL is equal to L di dt plus Ri equals Vn cos of omega t, equation 2. Right. To resolve this, we've got to resolve it as a homogeneous equation. To make a homogeneous equation, we need to make the right-hand side equal to 0, and that is what we've done there. Right, the solution of this is similar to what we've done already in the analysis of transients in the first order RL and RC. If you review the notes there. Alright, so just quickly, so how do we go about this? It's just L di over dt is equal to minus Ri. So di over I is equal to minus R over L dt. Right? And of course, this we need to integrate to get rid of the differentials. Right? And that will give us ln I is equal to the constants come out, it's minus R over L t plus a constant which we name ln k. And so putting, that ln I minus ln k, right, is simply equal to ln I over k, and that is equal to minus R over L times t. Right. To remove ln, we know that we've got to raise it to the exponential. So e to the power of ln I over k. Whatever we do to the left hand side of the equation, we must do on the right hand side of the equation. Right. That's equal to e to the minus R over L t. Right. This, of course, simply I over k comes in, so we can just apply this a and cross multiply with the k, so it becomes k e to the minus R over L times t. Right, so what we have in here as a general solution. Right. Now, if you have a look at the notes, instead of k, they use the constant a. So we can simply, instead of having that as k, we can put in a. We can put in a here. And of course, a over there. Right. Just to be consistent. A, and that is O, and that is A. Okay. So that is our general solution, which is there at the bottom of page 11. And this is also what is referred to as the complementary function. General solution or sorry, I've jumped a step ahead here. Leave out general solution. This is your complementary function. Alright, so now that we have that, let's go on to the top of page 12. Right, it says in there, what we have to look for now is the particular integral. Right? So for the particular integral, we have to consider the forcing function which is on the right hand side. And that forcing function is right over here. Vm cos of omega t. Right? So this tells us, when you work through that we will need to have this as, to resolve this, to have I of t, because it consists of a sinusoidal function, that it has got to have a constant a times cos omega t plus, sorry, it's just to be consistent with the notation in the notes. We will use b here. Sorry. I'll write that when it's dry. Plus c sine omega t. So it is. The cleaning fluid is mucking this bit up, so let me just see if I can dry this up a bit. Right, b cos omega t. So that will then have to be, we will then take this and put it back into equation 1 here. So we substitute in equation 1, right? And of course into the form that is there in equation 2. So you will then L di dt, so you differentiate that, plus r times I, which is just r times that, is equal to Vm cos omega t. And I'll leave that to you as an exercise. Right? And the answer that you'll get is what is given there as your full solution. Right? The full solution is I of t is equal to a times e to the power of negative r over lt. Right? So it is that plus b cos of omega t plus c sine of omega t. Okay. And the form that it'll take as a waveform, should you sketch that out, is what we have there on your notes. And you will see that it seems to be a decreasing function, right? That decrease is of course due to the fact that you have a transient there, which is this one here. Right? That's your transient. Right, you'll see that there's a negative in front of it, so that causes it to decay and results in that curving nature of that sinusoidal waveform. So in the bottom there, it simply says, if you assume, take two values of R and L, where R is 100 ohms, and L, if R is equal to 100 ohms, and L is equal to 25 millihenries and substitute it into that, you will get R over L is 4 milliseconds, 4 by 10 to the minus 3, and what you will get is, after only 1 milliseconds, right, what you will have is 0.018. So it doesn't last for long. So it is only there for a while, and then the steady state takes over. So this is your transient, and this portion of here over here takes over, because this is what then goes on to infinity. So hence the reference to it as a steady state. Right, so at the steady state, right, is what is referenced to at the bottom here, your steady state as I of t. Your transient here lasts only for a very short period of time, and what persists is your steady state, that b cos omega t plus c sine omega t. We will now take a short break.